So this is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful and appropriate, and please participate. But again, please do not share any contact or social media info during class for your own security reasons. You can still share things like what you like or your animals and stuff like that. But again, we don't want to be sharing contact information for your security as well as for our legal reasons. Okay, so let's go ahead and do a quick brain stretch. You have your whiteboard tools. Please circle the correct answers. You can do any of these boxes that you know. Try to do as many as you can, or make an educated guess and just guess and see what happens. All right, so I want to know, what are attendance checks worths? What are the analyses, lab reports, and exams worth? A homogeneous mixture or a solution, does it look different or the same throughout, right? Not uniform or uniform. A compound like carbon dioxide is a pure substance, so does that mean it can or cannot be broken down physically? And if it is a compound, does that mean it can or cannot be broken down chemically, right? So physically versus chemically. And then the total quantity of matter and energy in the universe is always changing or always the same. Remember, this brings us back to the conservation of the matter, conservation of energy. Go ahead. Let's take a look at what we remember from yesterday. If we have some mistakes, we'll correct those mistakes and we will learn from those mistakes. That's how learning happens. Awesome. All right. Looks like we are on track with a lot of this. Let's see who I've got on the board. Excellent. I see Hallie. I see, sorry, Hallie, make sure I'm saying your name correctly. I was looking at how you pronounced it in your survey and it still wasn't clear to me. So let me know. Okay, perfect. All right. Let's get, I see Trinity on the board. I see Nichelle, Vanessa participating. I see Junior there, Aliana. And let's see here. Jaden's on the board. Perfect. Yes, okay, gotcha. Yes, if I ever say your name wrong, please call me out. Please let me know. It's not okay for me to say your name wrong, so make sure you're letting me know. Or if I call you by the wrong name, again, remind me. I tried to remember all of them, but it is a little bit hard. Cool. All right, so let's go ahead and take a look at this. So how much of your grade is attendance checks worth? Yes, attendance is 10% of your grade. Remember, can you get this if you are not attending classes, right? This is not a trick question. Can you get your 10% if you are not attending classes? No, you have to make sure that you are attending classes so that you get the start of class word and end of class word for those attendance checks. And then analyses, lab reports, and exams, yes, those are worth 65% of your grade. They're a huge part of your grade. If you don't do any of these, can you pass the class? If you don't do any of these, can you pass the class, yes or no? Old students, you should definitely know this. No, you cannot pass, right? What's the maximum grade you could get if you did not do analyses, labs, reports, and exams? What's the maximum grade? Take 100 and subtract 65. Yes, you get 35, right? So a max grade you could get would be 35%. Although if you did do all the extra credit, you could actually get 45%, but still that would not get you to passing. So remember, these individual assignments are actually each worth about 4% of your grade, whereas notes are worth about 0.5%, and attendance is worth like 0.3%. So in reality, you really want to be focusing on these big assignments. And today we have a lab report, so we're going to go ahead and do that today. It's going to be worth 65% of your grade. All right. A homogeneous mixture, remember this prefix homo, we should be able to remember that this means same. So homogeneous mixture looks the same throughout. This would be like sugar dissolved in water. It tastes the same at the top, at the bottom, at the middle, and looks the same throughout. It's exactly uniform throughout the entire solution. Anytime we have, in your old classes, did you do attendance check in the recordings? So it used to be that, attendance was not required by Insight, and so I would have it as extra credit whether you either attended class or watched the recordings, and so it was in the recordings. But now I can't do that because it is actually a required part of the grade, right? So that's why we got to specify that. All right, compounds like carbon dioxide, remember, they are pure substances. Anytime we have pure substances, this means you can't physically break them down, right? You yourself cannot physically pluck off carbon from CO2. As great as that would be, and as cool as that would be, it'd be a pretty awesome magic trick. You can't do it physically, right? Yeah, exactly, Nichelle. A compound like carbon dioxide, on the other hand, because it is a compound, this actually means that it can be broken down chemically, right? It's made up of different chemicals. Do you guys know what C and O stand for? Tell me in the chat box, what does C stand for and what does O stand for? Think about CO2. What does carbon dioxide stand for? It means two different atoms here. What's the C and what's the O? Yeah, so we've got oxygen, 2 oxygens, that's what that 2 means, 2 oxygens, and carbon. So because we have different atoms, they actually can be broken down chemically, and we can undergo chemical reactions to break apart this carbon dioxide, right? Okay, now if it was a pure element, which is just like carbon or just oxygen, that would not be able to be broken down, right? So cannot be broken down is things like elements, like gold or silver or copper. Okay, the total quantity of matter and energy in the universe looks like we chose is always changing. However, remember we talked about the conservation of energy, and conservation means what? Conservation means what? Tell me in the chat box. 4-letter word that starts with S. 4-letter word that starts with S. Yeah, it means to save. So if we're saving the amount of matter and energy in the universe, do you think it's always changing or staying the same? If we're saving it, does that mean it's changing or staying the same? Yeah, it means it's actually going to always be the same, right? So even though it looks different, right, it might go from hydrogen and oxygen into water, or oxygen and carbon into carbon dioxide, bye-bye. Or it might be changing from heat energy to light energy to electrical energy. Even though it can change forms, the actual quantity actually always stays the same. Go ahead, give me a sun if that makes sense. Sun, if you understand that, the total amount in the universe always stays the same. I know that we did make a mistake, but we're correcting that mistake. We're learning from it. Perfect. Okay, so please make sure at this point, if you haven't already, make sure you open up your attendance check. Please enter the start of class word, which is right underneath that link, and then I need your green checks letting me know that you have done that. So still need some green checks. I need one from, let's see here, Albert and Junior, and green checks, please. Alexis W, Twan, Brandon, Chloe. Let's get a green check from Christian, David, Susan. Perfect. All right. Looking good. All right. So remember, here's my contact info. Remember, you do get 3 attempts on every assignment. We are doing our first big assignment today. It's going to be worth 65% of your grade, right? So today's lab is a huge part of your grade until we start adding more of them. So that being said, if you don't do well on it, make sure you try again. Okay. So today is day 4. We're taking a look again at the Viscosity Lab. Tomorrow, we will have optional support in Zoom. Remember that Zoom link is underneath the class plan, or you can find it in the plan tab for Wednesday. All right, so if you want me to go through it with you step by step, absolutely come to support, and I can do it step by step. That's a great way to get 100% on your labs, just as a helpful hint. And then we will be starting Unit 2 tomorrow, and we'll have our first analysis on Thursday. All right, so again, today's lab, because we only have one lab, that means this one lab actually takes up this entire 65%. So this means that if you don't do your one lab, you will not have a passing grade. All right, go ahead and give me a basketball if that makes sense. All right, so this is literally, currently we only have the 1D lab. So we got to make sure we get it done today. Perfect. Okay, so again, it's impossible to pass if you don't do these because they are a huge part of your grade. Don't forget, Star 360 is due this Friday. Okay, you have to make sure you do both reading and math in order to get full credit. Okay, and we want you to do them by this Friday because that's when leveling happens, which means if you do really well, you end up with less live sessions for the rest of the quarter. Okay, if you do really poorly or if you go through it too fast because you're not actually trying on it, you will end up with the maximum amount of live sessions and the maximum amount of attendance required. So try to do your best, go through it at your own pace, be careful, all right, don't fly through it, actually try your best on it, okay? And don't forget, make sure you're checking your grades tab daily. I do update that every day. That's where all your links are. That's where all your grades are. So really, again, you don't need to know how to use anything in my course except for the grades tab. All right, so we've been taking a look at the nature of matter. All right, so we've been talking about how matter gets classified. We talked about energy yesterday. Today we're going to talk about viscosity. So let's jump into this. We should be able to design an experiment based on a hypothesis, graph and analyze the resulting data. And we're going to be taking a look specifically at physical changes today. So we want to know what's the difference between a physical and a chemical change. And the physical change we're going to be looking at today is viscosity and how it's related to temperature. All right, and here is our agenda over here. So let's go ahead and jump into that. The first thing I want you to do, though, is to open up your lab report, okay? So your lab report is going to mean that you're going to have 2 tabs open. If that doesn't work for you because your computer can't handle having Blackboard and 2 tabs open, just be ready to take pictures. But give me a green check once you either have it open and ready or you're ready to take pictures. So again, taking pictures is totally fine, right? You can get all the answers and then work on it after class. The green checks again. Once you've got it open or you're ready to take pictures. Hi, Ari. Go ahead, open up your lab report. That's what we're opening up right now. If you're ever watching the recording, again, you can find it in the grades tab, obviously, once it's updated, and then you can also find it in the content tab. So content unit 1, scroll down, find the 1D lab. Perfect. All right. Looks like everybody's able to open it. Doesn't look like we're having any issues. Yes, Isabel, I sent the link in the chat box. So you can absolutely get to it right from the chat box. Just click on the link. Or again, you can go to content, unit 1, scroll down. Perfect. All right. Give me red X's if you're having any issues. But again, it's totally fine to either have it open or be taking pictures. And again, I will be giving you the instructions for the lab step by step. Today's lab is actually unique because I actually also give you all the data. So it's super easy. Make sure you follow along with us today. So let's go ahead and talk about physical versus chemical changes. Let's do a quick brainstorm. Think back to our spaghetti and meatballs example from yesterday. I want you to take a look at these different steps, and I want you to think about if you had to separate them into 2 separate groups, what would make the most sense? Okay, so we've got a bunch of different things. We've got chopping onions, breaking the spaghetti noodles apart. We've got baking meatballs, simmering the sauce, cooking the noodles, sauteing the onions, boiling water, mixing the meat, mashing tomatoes. What kind of 2 categories do you think these different things could fall under? Tell me in the chat box. Take a look at these different steps. Tell me what kind of groups do you think that these could fall under? Right? Do you think chopping onions would go with breaking spaghetti, or would it go with baking meatballs? Would it go with simmering sauce, cooking noodles? Yeah, so we've got ingredients, right? So let's take a look. We've got some ingredients like taking a look at onions and the spaghetti. What else counts as an ingredient? Just preparing an ingredient. Tell me in the chat box. Here, we can go ahead. I'll give you whiteboard tools. Go ahead and circle the ones where we're just preparing ingredients. Go ahead, circle the ones where we're just preparing ingredients. Yeah, exactly, right, Janice? So we've got mixing the meat, mashing tomatoes, yep, boiling water. So think about simmering, baking, and sauteing. Are those actual preparing the ingredients, just getting the ingredients ready? Tell me in the chat box. Simmering, baking, sauteing, are those just getting those ingredients ready to go? So this is actually like heating them, right? Or what's another word for that? What's another word for baking, sauteing, simmering, cooking, right? Or sorry, that's actually the answer. Right? So we've got 2 groups. So our first group is just preparing ingredients, right? So that's things like chopping or breaking, or boiling. I know that's not how you spell breaking. Boiling water. We've got mixing, mashing. Those are all just preparing ingredients. So what's our second group? Tell me in the chat box. What's the second category? We've got where we've just prepared the ingredients. What would be the second category? Take a look at what's left over. Yeah, cooking them, right? So actually getting them cooked, right? Because you can't just eat raw onions that are chopped. You definitely shouldn't just eat the meat that's been mixed. So instead, we also actually need to cook the food. All right, so that's going to be things like simmering or cooking or sauteing or baking. Those things all cook them, all right? So let's think about this. Again, this first kind of group that we created here, that first group is just kind of changing how the ingredients look, but are the ingredients themselves actually changing chemically? Tell me in the chat box. Are the ingredients themselves actually changing chemically? Are they changing at all, like in terms of how they taste, how they feel? No. So the only thing that's changing, right, is kind of whether or not they're big or small, right? But it's still the same exact stuff, the same exact food. Now, question number 2, though, or group number 2, is the actual, like, how the food tastes, how it's been prepared. Now, does it change? Once we've cooked it, does it change? Yeah, totally, right? Think about how meat goes from like pink to brown, and you can't make it go in reverse, right? So it goes from pink to brown, it's been cooked. That's an actual chemical process. Or think about simmering or sauteing onions, right? When we saute onions, they go from like white and really smelly and they make you tear up, and then they get sweeter and they get browner, right? Same thing with simmering or baking or cooking, right? It's changing what those things actually look like, what they taste like. It's changing them fundamentally. Go ahead and give me a, let's see here, give me a music note if that makes sense. All right, so we have two groups here, just preparing and then cooking. They're different things though. Let's take a look at what that means. Hi, Andrick, welcome to class. Make sure you open up your lab report. All right, so this brings us to chemical versus physical changes. So chemical changes mean that matter can be converted from one form to another by changing the actual bonds, right? Where are my matches? Oh, here they are. Perfect. All right. And so this actually creates different substances. For example, lighting a match. All right. So take a look. Here is the chemical equation for lighting a match. We have in the tip what's called tetraphosphorus trisulfide, and then we also have potassium chlorate, and when you add a spark or friction, they ignite together and they create something totally different. So they create diphosphorus pentoxide, they create potassium chloride, and sulfur dioxide, which is the smell of a match. How many of you like the smell of a match? I definitely do. I like the smell of fire, right? So if you take a look at this, right, you can see it starts out green and kind of unique looking like that. Oh, sorry, one second, guys. Definitely just threw that match onto my desk while it was still lit. Let's try that again. That was exciting. Got a little bit of adrenaline there. All right, so what we can see is they actually begin to react together, and they create a flame, right? So there's definitely a reaction going on. And then if you look at this afterwards, it looks totally different and it smells totally different, and we can see that there's different things that have been created. Go ahead, give me a smiley face if that makes sense. Smiley face if that makes sense. This is a chemical change. We have fundamentally changed those chemicals into different chemicals, okay? Now, another example would be if you take sucrose, which is a type of sugar, and potassium chlorate, okay, which is another chemical. They react very violently together to produce totally different compounds in a really cool way. So they create carbon dioxide, they create potassium chloride, and they create water. So this is a crazy cool crazy cool video that I'm going to go ahead and show you right now. So let me go ahead, grab this video. Hopefully it works, because apparently SafeShare has been having some issues today. And give me a green check when you finish watching it. I think that bear went to heaven, actually, Junior. I don't think he went anywhere. Yeah, that was super intense, right? It got serious really fast. That poor bear. Make sure you give me green checks if you were able to finish watching it. All right, what were some observations that you made? It's a really cool video, right? What observations did you make? That poor gummy bear. Poor gummy bear. What did you see? Yeah, it changed colors. There was lots of smoke. I know. What did he do? He must have been a very bad gummy bear. There was like fire, right? You could see light. You could see explosions, right? The light was colored. It was a super cool color. It was like a pinkish color, right? I have a picture of it right here. So what's happening here is you're actually taking this sucrose. Yeah, it was a gummy bear, Antonio. So this sucrose is made up of sugar, hydrogen, and oxygen, which is what all sugar is made up of. You add this potassium chloride, and it creates totally new stuff. It creates carbon dioxide, potassium chloride, and water, right? Which is why we see that like gas coming up, because it gets really hot, and so that gas expands and it becomes steam and it shoots out, right? It's due to the color of potassium chloride, actually. All right. So again, we're changing things into different substances, but remember, we talked about this during our brain stretch today. Does the total amount of matter change? Does the total amount of stuff change from start to end? Does the actual quantity, the actual number of atoms, the actual mass, is that actually changing based on the conservation of matter? Does that change? Yes or no? Think about this word conservation. Is it changing? No. So again, the total amount of matter, the total amount of energy does not change. Only what it looks like changes. So again, it's chemical change because we're creating different substances, but the quantity still is the same. What's on the left still is the same mass as what's on the right. Okay? Now, physical changes, on the other hand, are when matter does change, but no new substances are chemically formed. So, for example, phase changes are physical. Think about when you freeze water or boil water, is it still H2O? Yeah, so the type of matter can change, Junior, right? But because the structure changes, but in total, the total amount of atoms stays the same. So when we talk about like the quantity, we're meaning the total atoms and mass stays the same from start to end. Yeah, so freezing and boiling water, are they still H2O? Yes or no? Are they still H2O? Think about the ice in your freezer. Think about the steam when you boil water. Yeah, it's still H2O. So if it's still H2O, this means that it's not a chemical change, it's only a physical change because there's no new chemicals, there's no different chemicals, right? If you crush something, if you melt something, if you mix it, it's still just physical changes, right? We can evaporate the water to get sugar back. So it's just a physical change. If you shred it, if you chop it, if you break it, right? That's like preparing our ingredients for our spaghetti and meatballs, right? Chopping those noodles or breaking those noodles, chopping the onion, all of those were just physical changes because chemically, the actual chemicals did not change. All right, so let's go ahead and make sure that makes sense. Match these up. We've got physical changes, chemical changes. I've got some examples and some definitions over here on the right. Please use your whiteboard tools. Please use thin lines, any color but red. So it's the third from the last tool. That's your line tool. Please use thin lines and any color but red. Any color but red. All right, what are physical change examples? What are chemical change examples? And what is actually happening? Are they making different substances or new substance, or the same substance? Different substances, or is it still the same substance? Whew, that's a tongue twister. All right, I see Vanessa on the board. I see Andrick and Jelly and Becca and Isabel, Hallie, and let's see here, Nichelle on the board. Thank you. I've got Brandon participating. Oh my gosh, too many names. Love it. Perfect. All right, let me go ahead and pause these tools, and this is going to be number 1 in your lab. Again, at this point, you should have your lab report open and ready to go. And let's go ahead and take a look at this. I'm going to grab my colors here. Let's grab some blue. All right, so physical changes. Yes, physical changes mean that it remains the same substance, right? So when we break spaghetti, that's just broken spaghetti noodles, but it's still chemically the same. When we freeze water, it's still H2O, so it's still chemically the same. Now, I do notice that a lot of you chose baking meatballs. Think about this. Can you eat the meat before it's baked? Can you eat the meat before it's baked? Tell me in the chat box. Can you eat the meat before it's baked? No, that would make you very, very sick. But can you eat it after it's baked? Can you eat it after it's been baked? Yes, so this means that when we bake meatballs, this actually chemically, or fundamentally changes them. Right? So what's really happening, I'll explain to you, what's really happening is we're killing off some bacteria, right? We're killing off some stuff that can hurt you, which is why we don't eat raw meat. But it's also actually chemically changing the meat. It's denaturing the proteins, so it's making it look different. It goes from pink to brown. It tastes different. It also can burn it, and burning is what's called the Maillard reaction. So it's all chemical reactions. Cooking is chemical reactions, all right? So this is actually not physical. So let's go ahead and correct that mistake. Let's use a different color here. So we've got chemical changes, again, make different substances like lighting a match, right? That creates totally different substances. We saw the fire. We saw how it looked different at the end. And again, cooking also changes it into a new substance. Go ahead and give me a 8-ball if this correction makes sense, right? We made a mistake, but we corrected it. We're going to learn from it. Perfect. This is number 1 in your lab. I need you to either take a picture of this or complete it in your lab report. You have let's see here, 45 seconds, green checks when you're ready. Sorry, let me clear out your old ones. Green checks when you're ready for me to move on. Need green checks from Junior and Alexis W. Tuan. Ari, green checks, please. Waiting on Danny and Christian. And Jelly. Jorge, green checks. Saw some random guy eats raw meat every day. Said he was 100% healthy. Yeah, I mean, so that's what's called anecdotal evidence, right? So statistically, that means that like the majority, like if you start eating raw meat, you will like the statistics for you getting sick will go up. That doesn't mean everybody gets sick, right? There will be some healthy individuals, but it's still not good for you, right? Yeah, definitely rather cook it. It tastes better when it's cooked anyways, right? I would think. All right, cool. So now we're going to go ahead and talk about today's lab. So today we're going to be taking a look at viscosity, which is a physical, yeah, exactly. It is a physical property. Even like when you eat steak like medium rare, it's still a little bit raw. So you're reducing your risk because the outside is cooked, which is where the majority of the bacteria is, right? But you're still increasing your risk slightly of getting sick. Again, most people don't get sick, but again, if you look at the data, you're actually increasing your risk a little bit, right? So anyways, viscosity is a physical property because it's the resistance to flow or how difficult it is to make something move. All right, so think about, for example, honey. Honey has a really high viscosity. It's more difficult to make it flow. It's much thicker. It flows more slowly. Go ahead, give me a smiley face if that makes sense. Smiley face if that makes sense. Honey is high viscosity. It's difficult to move. It's thicker. It flows more slowly. Cool. Water, on the other hand, it has much lower viscosity. It's less difficult to move. It's much runnier, and it flows super, super quickly. Okay. Now, this is a physical property, right? Because even if you try to change honey's viscosity, it's still made up of the same chemicals. Think about this. Let's say you've got some honey in your bottle, right? And it's not coming out. What do you do? Tell me in the chat box. What's the solution when your honey is stuck inside of the honey bottle? What do we do? What do we do to get it out? Exactly. I see Trinity answering. I see Vanessa, Becca, Nichelle, Jorge. Yeah, you warm it up, right? Yes, take off the cap. Exactly, Hallie. You can tap it, you can warm it up, you can heat it up. So exactly, a lot of people, what they'll do is they'll run it under hot water, okay? And so when you run it under hot water, it gets runnier or less viscous, less thick, less difficult to move. But is it still honey? Are you still putting it on your food because it's delicious? Yes or no? Yes, it's still honey. So even when it gets hotter and runnier and less viscous, it's still honey. So it's still the same chemical, and therefore this is only a physical change. So this is a physical change we're going to be taking a look at today. Please fill in the blank here with the word resistance and then give me a green check. You have 30 seconds to go ahead and complete that for number 2 in your lab. All right, still waiting on some green checks. Junior and Alexis W, Antonio, Tuan, Ari, Brandon. Thank you, Antonio. Waiting on green checks from Becca. Again, fill in number 2 in your lab with the word resistance, exactly as you see it here. Perfect. All right, everyone. So now we're going to go ahead and take a look at our lab. All right. So today's question that we're going to be looking at is, how does temperature influence viscosity? So how does the temperature of honey influence its viscosity, its thickness, right? Which I'm sure you already know about because we actually just talked about it. So the scientific method, again, if you were with me last quarter, this is familiar. If not, hopefully this looks like something you've seen before. But in the scientific method, what we do is we make observations, we ask a question, we form a hypothesis, which is an educated guess. We make an experiment based on that hypothesis, get the data, analyze the data, and draw conclusions. Was our hypothesis correct? Awesome. Was it disproven? In which case we need to change it and correct it. All right. So what we're going to do is we're going to use our senses to make some observations about the world, or to talk about observations that we have made about the world before. So David, I've always had contacts. It's just I haven't been wearing them because my eyes have been itchy, so I've been using my glasses for a while. But yeah, I've actually always had contacts. You can see it if you ever look at my old videos. All right, so take a look here. I've got some honey here. All right, this honey is warm, right? So tell me, how is it flowing? Tell me in the chat box. How does this honey flow? Quickly, slowly? Yeah, I wore my glasses all last quarter. Right? Well, I would say that it's currently warm, so it's actually flowing pretty quickly, right? It's not super slow, like it's not frozen, right? But now take a look, it's now on ice, and in comparison, take a look at when it's on ice, All right, now how does it flow? All right, it's been on ice. Tell me now, how does it flow? Quickly or slowly? Take a look at it coming off of my spoon. Yeah, it's not even moving off of my spoon, right? So I would say that when it was warmer, it flowed a lot faster compared to when it's on ice, it flows a lot slower, right? Go ahead, give me a smiley face if you understand that, if you agree with that, right? Look, it's totally stuck to my spoon right now. All right, cool. So some observations that we made, right? Out of the bottle, right? Warm honey. Warm honey pours pretty fast, right? Not as fast as like water, but it pours decently fast, right? I'm not going to be waiting forever. Whereas cold honey, like, barely moves at all. Barely moves at all. So again, today we're going to be taking a look at how temperature and viscosity, right, which is how difficult it is to move, are related. How these are related. Give me a green check if you understand where we're going today. Green check if you're beginning to understand what we're taking a look at today. Love it. All right. So our observation for today is when a fluid like water or honey gets heated, it becomes runnier, right? Warm honey is much runnier than cold honey. So how does the temperature of honey influence its viscosity, how difficult it is to move? So we're going to make an educated guess based on what we already know, right? Educated guesses or possible answers are educated based on observations that we've made in our lifetime. So if honey is colder, so if temperature of honey is colder, what do you think? Is it runnier or thicker? Is it runnier or thicker? Tell me in the chat box. Think about this cold honey. Is it runnier or thicker? Runnier or thicker? Yeah, it's definitely much thicker. Then honey will be thicker. And if it's thicker, is it more viscous or less viscous? Remember, viscosity is difficult to move, right? So is it more viscous, more difficult to move, or less viscous, less difficult to move? Yeah, it's going to be more viscous, more viscosity, more viscous. All right, good. Now, we could also say it the opposite way. So this temperature of honey is hotter, then what happens to the honey? Think about the warm honey that I poured from the bottle, right? Will the honey be thicker or runnier? Tell me in the chat box, thicker or runnier? Yes, then honey will be runnier. And so if it's runnier, is it more viscous, more difficult to move, or less viscous, less difficult to move? Yes, it is less viscous. Less viscous because it's less difficult to move. Awesome. Go ahead and give me a star if you understand this hypothesis. Star if you understand this hypothesis. This is where your lab is taking you today. Perfect. All right, everyone. So in this experiment, we have our independent and dependent variable. Now, if you weren't with me last quarter, I'm going to review those terms really quickly. So the independent variable in an experiment is what you change on purpose at the start of the experiment. The dependent variable is what you measure at the end of the experiment. Okay, so take a look at our hypothesis and take a look at the start of our hypotheses. All right, so tell me, what's our independent variable? What are we changing at the start of our hypothesis, at the start of our experiment? Right, remember the beginning of this will tell me my independent variable. Are you all right there, Danny? Did the cat just run over your laptop? Yeah, so the independent variable here is going to be what? What are we changing? I got an answer from Vanessa. I see Isabel typing. I see Kara typing. Yeah, we are changing the temperature. So the independent variable is going to be the temperature of honey. Awesome. Now the dependent variable is what we're going to change at the end of the experiment. So let's take a look here at the end of our hypotheses. So at the end of our hypotheses, what is our dependent variable, or what we're measuring at the end of our experiment? Take a look here. This will be our dependent. What are we taking a look at? What's the result that we're looking for with our honey? Yeah, the viscosity. So the viscosity of honey, how difficult it is to move. Awesome. This is number 3 in your lab. Go ahead and give me a green check when you've either filled it out or you've taken a picture. You have 30 seconds. Ready, set, go. You can copy it exactly as you see here. All right, need some green checks from Junior, Kara, Alexis W, Antonio, Tuan, Ari, Brandon, Chloe, Chris, let's see here, Emily, Estella, Jarrett, Becca, Trinity. Green checks, everyone. Again, this is the answer to number 3. I'm giving you the actual answers, word for word. So please pay attention. Please fill out number 3. Awesome. All right, looking good. Let's keep on going. All right, so just talking about this lab. So this is a video lab, and so you're going to be watching the video for the lab, and then I do actually give you all of the data. Please give me a thumbs up if that makes sense. I'm giving you the data. You're going to copy the data exactly as I show you in the video. Exactly as I show you in the video, okay? Perfect. So the video includes step-by-step instructions on how to complete numbers 4 through 6, okay? So I know it can be a little bit intimidating if it's your first time doing one of these labs. Please be aware you do need a Google account. I do go over in the video how to make a Google account. And then the video does have the instructions for every single step. All right, so after every step, pause, complete it in your own lab report. You're going to be filling in a Google template with your data. Again, it will be data that I give you word for word or number for number. I give it to you. And then it will explain how to fill out your conclusion and how to fill out your prediction using your trend line. So there are 4 more questions, but the link goes over all of it. Hello, students. At this point, you should have already answered questions 1, 2, and 3. All of those answers were provided word for word in class or in the recording of the class. So now we're going to go ahead and move on to questions 4, 5, and 6. 4 is where we actually graph the data that we got. 5 is going to be our conclusion, and number 6 is going to be the prediction that we used our trend line with. So remember that this is a video lab, which means the data is going to be given to you. So I'm going to go ahead and show you the video for how this data was gathered, and that's going to be really important to understand how we're going to graph our data. So let's go ahead and watch that now.
Hi, I'm Pat Keeney, an instructional designer with K-12. Along with my assistant, we're here to work with you on a lab that explores the viscosity of honey. In most lab work, advanced preparation is needed and safety is always important to consider. Viscosity is a fluid's resistance to flow. While substances, such as honey, are described as being viscous, all fluids can be characterized by their viscosity. Molasses, motor oil, and honey all have high viscosity. Water, juice, and rubbing alcohol all have low viscosity. In this lab, you will see how viscosity responds to temperature. The important question to consider in this lab is, how does viscosity change with temperature? Viscosity indicates the thickness of a fluid. Specifically, viscosity is a fluid's resistance to flow. In this experiment, we will warm up cold honey and then measure how it flows down a ramp to demonstrate how temperature and viscosity are related. Use your observations and prior knowledge to write a hypothesis that describes how viscosity changes when temperature changes. A good hypothesis should take the form of an if-then statement, such as, if the temperature increases, then, well, you finish the rest. Honey packets can be made in advance by putting 1 tablespoon of honey in 7 snack-size, zipper-closed plastic bags. Or you may obtain honey packets in a cafeteria or restaurant. Freeze the honey packets for several hours. We made a tray of ice cubes, which was needed to lower water temperature during the experiment. Before beginning the lab, we will create a data table with the following columns: temperature in degrees Celsius and distance covered in 30 seconds, measured in centimeters. We'll get our ramp ready by placing aluminum foil under one end of a cookie sheet to catch any spills. First, we tape a metric ruler to a cookie sheet lengthwise, with the 30-centimeter end near the bottom of the sheet. Then we add a piece of tape to create an easily visible reference point as a starting line. Now we're ready to get started. We put a thermometer in a large plastic container and then filled the container with water that was about 70 degrees Celsius, slightly colder than what is needed for hot tea. We then recorded the water temperature in the data table. We were concerned about some safety issues. For instance, if the water is too hot, it would melt the plastic honey packets. Never microwave honey packets. They will heat up extremely fast and the microwaves weaken the plastic. The packets may break when you handle them. Hot honey can cause bad burns because it sticks to your skin. To warm the honey, we placed a honey packet in the water for 5 minutes and then removed the packet. To get the best lab results, we sealed the packet securely before placing it in the water and dried the packet when we removed it from the water. This avoids mixing any water with the honey. Water may alter the viscosity of the honey and therefore could compromise the experiment. Next, we removed the packet from the water, dried it, and then used scissors to snip off the corner of the packet. With the cookie sheet flat on the work surface, honey was squeezed onto the sheet near the 0 centimeter end of the ruler. We lifted one end of the cookie sheet off the table and onto the container so that it was angled, allowing the honey to flow down the sheet toward the 30 centimeter end of the ruler. To get the best lab results, understand that certain things may vary, such as the honey itself, the indoor temperature, or even the type of cookie sheet. In the first trial, if the honey moves too fast or too slowly, we could increase or decrease the time of the trial, or tilt the cookie sheet more or less. After the first trial, we have to be sure to always use the same setup for each succeeding trial. Notice that we were certain to wipe all the honey from the cookie sheet. We repeated the entire procedure using water at approximately 40 degrees Celsius to warm the honey. Then again using room temperature water at about 20 degrees Celsius and in ice cold water at approximately 0 degrees Celsius. We used ice to lower the temperature of the water. You probably understood before beginning this lab how viscosity is related to temperature. Now that you have seen this lab conducted, you should be able to describe that relationship. You will be provided with data from this experiment and possibly others like it. In all cases, the same procedure has been used.
Okay, so at this point, we're going to go ahead and actually begin to graph our data. So you do need a Google account. Remember, if you don't have one, it takes about 30 seconds to make one. You need to go to accounts.google.com/signup. Please make sure that once you create your Google account that you do write down your username and password, because we do use our Google account the entire quarter anytime that we have to do a graph or we have to do an analysis or we need to do a drawing. We are going to be using the Google account. All right, so now what we're going to do is we're going to go ahead and actually begin graphing our data. So again, the data is being provided for you in this recording, so make sure you watch very carefully. So we're going to click this link that says, click here, viscosity data and graph template. All right, so this is in question number 4. Click on this link. And then click make a copy. So we're going to go ahead and click make a copy in order to make a copy of this template. So again, in question 4, click the link and then go ahead and confirm that you want to make a copy. So you can see here that we have a table on the left with some colors. That is the only place that you're going to be putting in your data. Do not change anything to the graph. The graph will update on its own as data gets entered, so please do not touch the graph. When we enter data into these boxes, please be aware that you should only be typing in numbers. Please do not put any units, like don't type degrees Celsius, because I already know degrees Celsius is up here, and it will mess up your graph if you include any letters or units in here. So please only put numbers into these 2 colored columns here. You should be copying the data that I will provide you in a moment. Again, I am giving you the data exactly as you should enter it. And then the last thing is, please make sure that you click outside of your last data box so that it saves. Remember that if you are typing into a box and you don't press enter or you don't click outside of it, it will be blank and you will lose points for that. Now, at this point, what I would like you to do is make sure that you type your name up at the top. So where it says type your name here, make sure that you type your name. For example, Johnny Appleseed. And again, click out of it so that it saves, just so that it's easier for me to grade and so I don't accidentally mix up your data with someone else's data, which could affect your grade. So now what we're going to go ahead, again, we're only going to type our data into the table with only numbers. And then we're going to check to make sure that everything looks correct. And then we will get the shareable link. The shareable link is what you get from the share button. Do not give me the link at the top. You will automatically get a 0 because this link at the top does not work for other people. It's your personal link. So you need to actually give me the shareable link. So let's go ahead and go through those steps. Okay, so here's the data that you're going to be entering. This is the exact data. You're going to copy this exactly as you see it here. Okay, now what's important to understand is that when we measure viscosity, we're actually measuring how far it runs down that ramp that you saw in the video, right? So this is how we're determining the viscosity, if it's runnier or if it's thicker, is by how far it manages to get down that ramp in 30 seconds. Okay, so this is still our dependent variable. Just be aware that it looks a little bit different than what we determined our dependent variable was originally, just because this is how we're actually going to physically measure viscosity. So remember, our hypothesis is if the temperature of honey is hotter, then it will have lower viscosity, meaning it will be runnier, right? It pours out of a bottle more easily. If the temperature of honey is colder, then it will have higher viscosity. It will be much thicker and harder to get out of the bottle. Okay, so let's go ahead, take this data, and we're going to copy it into here exactly as you see it. So for example, the first box you should fill in with 70 degrees or 70.0. And then the second box you should fill in with 7.2 centimeters. So it managed to get down the ramp in 30 seconds, a distance of 7.2 centimeters, which is a pretty big distance. The next box, we're going to go ahead and put 40, and then it only managed to get 6.1 centimeters. And so on and so forth. All right, so you need to enter the rest of this data. So you'll be entering 20, 5.3, you'll be entering 10, 4.7, and 0, 4.4. Again, make sure you press enter or click out of the last box so that it saves. Otherwise, you will lose a bunch of points for your orange boxes. Okay. And so you will see that over here, we can begin to see that a graph has formed. Again, don't touch the graph. The graph is automatically going to update. It's going to have everything you need. So we can see our independent variable at the bottom, which is our temperature in degrees Celsius. We can see our dependent variable over here on the y-axis, which is the distance covered in 30 seconds in centimeters. Again, this is how we're measuring viscosity, how runny it is. The further it goes, the runnier it is. And we can see our data right here. So we see our data that we graphed, as well as a trend line, which is going to help us make a prediction in question number 5. So again, make sure you fill out the rest of these. Make sure you click outside of the last box. All right, so now what we're going to go ahead and do is we're going to go ahead and get our shareable link. So again, you need to actually submit the shareable link, which we get by clicking the share button, clicking get shareable link, click copy link, and then paste it into this answer box right here. Again, if you do not give me the actual shareable link from the green share button, you will automatically fail this question because I will not be able to see your data. Okay, if you try to give me the link at the top, it will not work. So what we're going to go ahead and do, I'll show this to you, is we're going to again click the green share button. We're going to click get shareable link, and then copy link. Make sure that it says that anyone with the link can view. So then copy link. All right, so share, get shareable link, copy the link, and then you'll go back to your answer box and it says right here, paste the link into this answer box. You can right click and paste. You can also press Control and then V at the same time on a PC computer. Or you can press Command and V at the same time on a Mac in order to paste. All right, it will do the exact same thing. So for example, press Control, then press V at the same time, and that will also paste it. Okay, so that's your shareable link that you're copying from your Google spreadsheet. Again, make sure it's the shareable link from the green share button, otherwise I won't see it, and you'll get a 0 out of 60 on this very big question. All right, so now let's go ahead and do our data. So we're going to say, did the results support or disprove our data? And we're including actual numbers from our hypothesis. So let's go ahead and take a look over here. I'm going to go ahead and include my data right here. Okay, so the first part of hypothesis is if the temperature is hotter, then it will have lower viscosity and will be runnier. It comes out of the bottle more easily, right? And we want to know, is this supported or disproved by our data at like a hot temperature? We're going to choose one of the hot temperatures. We're going to say how far did that honey go? Does that mean the honey was thicker or runnier, and therefore did it have a higher or lower viscosity? Now, for example, you can use either 70 or 40. Those are both hot temperatures. So you would say 70 or 40, right? So for example, you could choose 70 or 40 degrees Celsius. Okay, and then the honey covered a distance in 30 seconds of blank centimeters. So if you choose 70, right, you would say it went 7.2 centimeters. If you chose 40 as your hot temperature, it would go 6.1 centimeters. And this means that the honey was thicker or runnier. Again, we talked about how the further distance it goes, the runnier it is, the more it runs down the ramp. So these hot temperatures, you can see, have much bigger distances. So I'm going to go ahead and say that these ones are definitely going to be runnier. And if they're runnier, this means that they are going to have lower viscosity. Remember, viscosity is how difficult it is to move. So if it's runnier, it's less difficult to move, so it's lower viscosity, right? So lower viscosity, runnier, and then remember, we're choosing hot temperatures like 70 degrees or 40 degrees. And so if we have hot temperatures that are runnier with lower viscosity, you can see our hypothesis said hot temperature, lower viscosity, runnier, and so this would be supported. Okay, so again, this is exactly what yours should look like, but make sure you include your actual data. So 70 degrees and 7.2 centimeters, or 40 degrees and 6.1 centimeters. Either of those will work as your hot temperatures. Now, the second part of your hypothesis is the opposite, right? So we're going to take a look at the cold temperatures. If temperature is colder, it will have higher viscosity. It will be thicker. In other words, it's harder to get out of the bottle. All right, and so we're going to go ahead and choose a cold temperature. We can see our cold temperatures down here are 10 degrees and 0 degrees. All right, so choose either 10 degrees or 0 degrees. And then the honey covered a distance in 30 seconds of, let's go ahead and write down the resulting distance, right? So if you choose 10 degrees, the distance was 4.7 centimeters. If you chose 0, the distance was 4.4 centimeters. Okay, and so this means that the honey, was it thicker or runnier? Again, if it only went a really, really short distance, this is definitely going to mean that it is thicker. Right? So it's definitely not as runny because it can't get down the ramp quite as far. And so if it's thicker, think about, does that mean it has higher or lower viscosity? Right? We know runnier means lower viscosity. So what does thicker mean? What's going to happen to its viscosity? Again, think about thicker fluid, right? So is that higher or lower viscosity? And then we're talking about cold temperatures. So if all of your answers end up being consistent with this, where it's cold with a higher viscosity and thicker, then you would also write supported right here. Okay, if it's different, you would write disproved. And again, make sure you include your actual data. So your actual data should be either 10 or 0 degrees Celsius, and the distance, which was 4.7 or 4.4 centimeters. And again, you need to figure out, what does thicker mean? Is that higher or lower viscosity? And is that consistent with your hypothesis? If so, it's supported. If not, it's disproved. All right, so that helps us to draw our conclusions, right? Hopefully we do support our hypothesis, since this is something that we have seen throughout our lives. So if this is supported, then remember that this scientific method says that we can go ahead and move on with this, right? Communicate our results. If our hypothesis is disproved, then we would need to go back and change our hypothesis and repeat the scientific method to figure out what's really happening. Okay? So that's question number 5. You should be able to fill in the rest of this on your own. And then question number 6 says, let's go ahead and use our trend line to predict how far the honey flows at 80 degrees Celsius. Now, please make sure you actually use your graph trend line after you have filled in all of your data, right? So make sure all your data is completely filled in, including that last box. Make sure again that you click out of this last box and press enter. So you should have 5 data points. If you don't see 5 data points, you haven't done it correctly. All right, so if honey is heated to 80 degrees Celsius, then you'll predict that after 30 seconds, it will flow a distance of blank centimeters. So we're taking a look at our graph right here. Let's go ahead and copy this. Okay, and you can see at the bottom that we have our temperature, which is 80 degrees Celsius. So we're going to go ahead and start at this 80 degrees Celsius. And again, you need to actually do this on your own graph once your data is actually completed, because otherwise it will not look the same as mine, right? So you're going to go ahead and then look straight up until you hit the trend line, which is how we make predictions. And then once you hit the trend line, you're going to look straight to the left, straight to the side, all right? So straight to the side right here. Now keep in mind that these little increments are 0.2, right? So this one is, sorry, so let's go ahead. So this top one right here, this bottom one right here is actually 7.2, right? And then the next one is 7.4. And then the next one is, sorry, 7.4, 7.6, and 7.8. Okay. 7.8. All right, so that's what those little dashes means. So this first little dash is 7.2, the second little dash is 7.4, this third one is 7.6, and this fourth one is 7.8. And then obviously we have 8, right? All right, so take a look very carefully. Wherever this hits on the left side, that is the distance covered in 30 seconds. And so that would be your number of centimeters that you would predict. So take this number, and that's what you would type into here. Again, make sure you use your own graph because my graph is not complete, and so the data is not yet correct. All right. And that will help you fill in this one. All right. It should be somewhere, hopefully really close to what you see here though, based on our data that I already have. And then make sure you submit, and then it will ask you again to submit a second time. Make sure you confirm that. Otherwise I won't get it and you will get a 0 on this. Thank you so much everyone, and I will see you later. One last time, go ahead and give me a smiley face. Give me a cool face if that makes sense. Cool face if that makes sense. And then I'm going to go ahead and send the link out. Love it. All right, so here is the link to the video right here. Obviously, we are out of time, so I'm going to go ahead and just wrap us up. Again, please watch the video. If the video is still too confusing, come to the support session tomorrow, the Zoom session tomorrow, and we can go over it together, okay? Give me a green check if you feel comfortable with that, red X's if you don't. All right, again, the video goes over how to do 4, 5, and 6 step by step. So just watch it, go through it at your own pace, do what you got to do. Cool. All right, so we talked about the experiment hypothesis. We talked about you'll be taking a look at how to graph and analyze the results. We talked about physical versus chemical changes and viscosity and its relationship to temperature. How are you feeling about this? Point for me on the board. Where are you at in terms of talking about physical versus chemical changes, viscosity and temperature, understanding our hypothesis? Love it. Again, make sure you watch this YouTube video. Looking good. Let me pause that. So the lab report is technically due at 4 p.m., but I do give you about 48 hours before I enter zeros. So make sure you just do it correctly, right? You don't have to get it in exactly by 4 p.m. today. I won't penalize you for that. Try to get it done though soon, because I will be entering the zeros tomorrow, or what is it, Thursday, before we do our analysis, before our next big assignments. All right, so I'm going to stop our recording here. And then here is your last word for your attendance. Thank you so much, everyone. Have a wonderful day.